Now that we know the chain rule, let's just practice using it. Let's say I want to take the derivative of the square root of tangent of x. Now, I can see that's a function composition. I'm plugging tangent into the square root function. So probably before I take the derivative, I'm going to want to rewrite that as tangent of x to the 1/2 power, because I always rewrite my roots as fractional exponents. And now I basically work my way from the outside in. I'm going to take the derivative of the square root part first, okay? And so I'm going to say, okay, that's going to be 1/2 of my input to the negative 1/2. But what was I plugging into that 1/2 power function? What I was plugging in was tangent of x. And then I've got to multiply by the derivative of tangent of x. I kind of like to just write that I have to come back and do that. That prevents me from making a very common mistake, which is to take this derivative and try to plug it in here. I'm never plugging a derivative into another derivative formula. I'm always just multiplying by the derivative of the inside part. So this would be 1/2 tangent of x to the negative 1/2 times the derivative of tangent would be secant squared. Okay. So you'll notice f is the outside part. I always start by taking the derivative of that outside part evaluated at the inside part. If you're ever not sure which part do you need to work with first, ask yourself what you would do in evaluating things. If I were to evaluate this, let's just say at pi over 4, I wouldn't take the square root of pi over 4. I would first plug that into tangent. So I would take my x, I would plug it into tangent of x, and then once I've done that, I would plug into the square root function. That's the order in which I would evaluate things. In taking the derivative, we go in the reverse order. Okay. Now I'm just going to show you a notational option for working with this. Okay. If I wanted to, I could give this inside function a name. I could call it u. So we sort of did this when we were looking at the gears, where we let u be the number of times that middle gear was spinning. That was our inside part. I'm just going to name that u. And then I can rewrite this as the derivative of the square root of, just the square root of u, which would be the derivative with respect to x of u to the 1/2. Okay. Now what that does is it makes it look simpler. This just looks like a sort of complicated expression. This looks a lot simpler, but I notice something here, which is that the variable with respect to which I'm taking the derivative and the variable in terms of which I've written this function do not match. That, plus the fact that I just gave it a name, reminds me that, okay, that's just a name for the inside part. And I know if that's the inside part, I'm going to need to know its derivative, because part of the chain rule is always to multiply by the derivative of the inside part. So if I name the inside part, I can go ahead and write its derivative. Then what I can do, if they don't match, this is going to be a two-step process. I'm going to take the derivative as if u was my variable. That's the derivative of the square root function at u. And then I know I have to multiply by u prime. This was a chain rule because these guys did not match. Now, the original problem was given to me in terms of x. I've now got my answer in terms of u and u prime. I want to go back to the original variable. So then I would just substitute back in. 1/2, u we said was tangent of x to the negative 1/2, and u prime is secant squared x. Some of you may find that that notation, that substitution of calling that inside part u, is helpful for you. You're certainly welcome to use it. Okay. I would suggest that all of you try some of the problems using this substitution method, even if you don't find that you think it's necessary all of the time. The reason is just that that's going to help us when we get to implicit differentiation, which I haven't taught you yet, but that's in the next section. We're going to see a lot of this where we're taking a derivative with respect to one variable of something that's expressed in terms of another variable. So good to get a little bit of practice with it. But you don't necessarily need to use this. This notation can become kind of cumbersome if you have more than one function composition going on. So I would practice sometimes using it and sometimes not, just to familiarize yourself with that option.